we shall discuss yet another special relation, namely functions. Consider the sets A and B, say A as 1, 2, 3 and B as ABC, and cross product A cross B as all possible pairs 1 comma A, 1 comma B, and so on. 2 comma A, 2 comma B, and all that, and so on up to 3 comma C. We know that any binary relation is a subset of A cross B. So we are going to define a special relation or a relation satisfying some property, which we call it as function. What is that? It is also a relation. It is also a relation which is subset of A cross B. What is the condition? Condition is this, such that for all A belonging to capital A, there exists exactly one B in B such that A comma B belongs to the relation is F in this case. So what it says is, we say F is a function if for all A in capital A, there exists exactly one B. This notation says unique B or exactly one B. Exactly one B in capital B such that A comma B belongs to F. Let's look at a couple of examples. Easiest way to visualize function is through the underlying graph model. You take A and B like this, and A represents 1, 2, 3, B represents A, B, C. A and B can be same, so you can have 1, 2, 3 here as well as 1, 2, 3 here. Nothing wrong. We are defining it considering A and B are two arbitrary sets. What it says is, for each element you find exactly one B. So this is an example of function. Let's look at this 1, 2, 3 A, B, C. It only says unique B, and this is also a function. Two elements over here can be mapped to same element. Nothing wrong. And you may leave some elements without any mapping. That is also acceptable. So I talk about mapping. So this gets the name domain. This gets the name codomain. Here is an example of another function. So you have 1, 2, 3 A, B, C, and all of them are mapped to just one element. This is also an example of a function. But consider this. You have 1, 2, 3 and A, B, C. Suppose A is mapped, 1 is mapped to something like this. Now this is not a function. Why? Definition says for each A, if you take A to be 1, it says there exists exactly one B. But if you look at f of 1 is it is mapping to A as well as B, which is not permitted as per the definition. For each of them there should be an image. That image should be unique, and each of them there is an image, but one is mapped to two elements A and B, which is not allowed. And look at this, say 1, 2, 3 and A, B, C. Okay. Now in this, is this a function? Answer is no, this is not a function. And 3 has no image. No image for the element 3. It says for each A in A, there should be exactly one B such that AB belongs to F. Here is an element for which there is no image. So when you look at 1 and A is image of 1, A is also image of 2, A is also image of 3. From this side, if you see, we say pre-image. So pre-image of A is the set 1, 2, 3. Okay. We also talk about something called range. What is a range of a function? For example, what all elements that this can see, that's precisely the range. So this is range, which means range of F is what all elements that the domain can see, which is A and B. Okay. Remember, as per this definition, this is not a function because this one is mapping to more than one element. This one is not a function because here is an element for which there is no image at all. Okay. And for an element, we talk about its image in codomain. For an element in codomain, we talk about its pre-image. It could be a set of elements. And for a function, we talk about the range. Range will tell you what all elements in codomain is covered as part of the mapping, is covered as part of the function f. So we see that range of f is a comma b. So now what we have seen is an example relation respecting some property, something like we have seen reflexivity, symmetricity and so on. This is also a property, it's also a relation. But the interesting part here is you are able to visualize the underlying sets like a bipartite graph with A as one of its partition and B as its another partition, and edges are from A to B. But one cannot have arbitrary edges, meaning these type of edges are not allowed, and one has some restriction on how the edges are going out from A to B. That restriction is defined by this. Fine. So although we looked at special graphs like bipartite graphs, there are other applications as well, but in the context of mathematics itself, just like relations, directed graphs, you see that functions and bipartite graphs are related. So what we look at is a special case of bipartite graph which is modeling functions, which is modeling these special relations. There are other interesting properties and counting which we shall see next. So consider a set A having say 3 elements and say B having 2 elements. Suppose we are asked to list all functions from A to B. Let's look at how many different functions are possible. Let's look at A and B. Suppose you have 1, 2, 3 here and AB here. So look at it from codomain. So this can be mapped to all of this. This is one function. This can be, B can be mapped to all of this. This is the second function. Or you see that A is mapped to 1, 2 and this is the case. So this is an example of a function, or 1, 2, 3, and A is mapped to 1, 3, and you get this. So what is that we are trying to do? We are looking at the possibilities for B. Fine? And that's precisely what we are exploring at each step. So we have 1, 2, 3 and AB. We looked at 1, 2, then we looked at 1, 3, then let's look at 2, 3. So 2, 3 is mapped to this, then B is forced. So we look at possibilities for this. So this is an example of a function. Like that, one can explore other functions. Okay. Now what is that we have done? We said 1, 2 is mapped to A, and the choice for B is forced. Now can I do the same thing for B as well? Say 1, 2 is mapped to B, then A is mapped to 3. So this is an example of a function. Then you have 1, 2, 3 and AB, and 1, 3 is mapped to B. So you get this. And the final one is 2, 3 is mapped to B and 1 is mapped to A. So you see that since you have got only 2 elements and there are 2 functions where only one element of domain is taken into account as part of the mapping. So that is taken into account. Then when you come over here and you know that there are only 2 elements here and 3 elements here. So naturally 2 elements out of this must be mapped to 1 here. Let me fix A. Now what are those 2 elements? We look at all possible pairs because we are listing all possible functions. So it could be 1, 2, it could be 1, 3, or it could be 2, 3. And these 3 we listed by fixing an element here. Now this can be other element also. That's what we have done here. 1, 2 and 1, 3 and 2, 3. The moment you say 2, 3 is mapped to this, there is no choice for A and the mapping for A is forced. So what is that we have precisely done is look at codomain. Codomain has got 2 elements and we are seeing possible functions, all possible functions in which what possible mappings that A can take and B can take. So in the sense that A can be mapped to any of this, correct? And A can be mapped to any of this. A can be mapped to any of this, correct? And in that sense, how many possibilities are there for A? How many possibilities are there for B? And that's precisely what we are interested in counting as part of this. And from this side, if you see, if you map 1 and A, then I should not use 1, or I should not consider 1 as part of counting when I look at other elements, because 1 and B is not allowed. Okay, I should focus on rest of the elements. 2 can be mapped to A. For example, 1 and 2 can be mapped to A, correct? So these 2 should be taken into account as part of our counting. So from this we see that each of this has got 2 possibilities. So this counting says there are 2 power 3, 8 functions. Now you see that each of this can be mapped to, so 1 can be mapped to this For f of 1 it is this. For f of 2 also it is AB. For f of 3 also it is AB. Correct? You look at one f of 1 is B. You look at one f of 1 is A. Even f of 2 can be A. For each of them you have these possibilities. So if you fix 1, 2, 3, what is that we are seeing? We are looking at possibilities of mapping 1 with respect to AB. It may be the case that it is mapped to this. It may be the case that this is mapped to this. It may be the case that this is mapped to this. So which means if you fix the domain 1, 2, 3, possibilities are this can be mapped to A or B, this can be mapped to A or B, this can be mapped to A or B, which means how many different functions are possible. First one can be mapped to two of them, that will give you two different functions. Second one can be mapped to two of them, that will give you another two functions. So like that you get 8 functions or 2 cube. So in general, what can we say? If there are say n elements in domain and m elements in codomain, then you see that A1 can be mapped to any of this. So which means A1, A2, so on up to AN, this can be mapped to any of this, B1 to BM. A2 can be mapped to any of these elements, B1 to BM, and like that it goes. Similarly, AN can be mapped to B1 to BM. That shows that number of functions is, for this there are m possibilities, for A2 there are m possibilities, so on up to AM. That tells you there are m power n. In general, it is cardinality of B to the power cardinality of A. There are this many functions from the domain A to the codomain B. So how many different functions are possible, with A being A1 to AN and B being B1 to BM is precisely this. Suppose you have got say 2 elements in the domain and say 4 elements in codomain, then you see that you get a function in which 1 and 2 are mapped to this. You get another function in which 1 and 2 are mapped to, say 1 is mapped to C and 2 is mapped to D. And like that you can start listing other functions. You get a mapping in which say both 1 and 2 are mapped to B itself. So you see that you have 4 possibilities for this. You have another 4 possibilities for this. So in one mapping you get to see that both are mapped to A, and in another mapping you see that both are mapped to 2 different elements. It could be CD, or it could be BC, or it could be AD, or it could be AC, and you look at all possibilities. So in general you see that it is this many functions, or you see that cardinality of B to the power cardinality of A number of functions. So interesting part over here is each of this is a relation. So that's something one has to relate, right? Let's do that. If cardinality of A is n, cardinality of B is n, then number of functions is n power n. How many relations are possible? Number of different binary relations. We have already counted that it is 2 power n square. Correct? Because size of the cross product is n square and any subset is a binary relation. So number of binary relations is precisely this. Note that function implies relation and converse need not be true. A binary relation need not imply function. For example, you have 1, 2, this side also say 1, 2. Okay. Now 1 comma 1 and 1 comma 2 say 2 comma 1. Fine. This one is a relation, but this is not a function. So relation need not imply function. So which means every function is a binary relation and converse need not be true. Which means you please check that n power n is less than 2 power n square. So number of functions is only a subset of number of binary relations. Therefore, this number must be respecting this inequality. You check that n power n is strictly less than 2 power n square.